Hey folks, my name is Nathan Johnson. Welcome to Lecture 11 of Vector Calculus, which is all about vector fields. In particular, what we're going to be talking about in this video is, well, what a vector field is and how we can visualize it. And then we'll just go through a couple basic examples. Okay, and then starting next lecture, we'll actually do things with vector fields. Okay, but let's walk before we can run. Let's start with the basics. What is a vector field? Okay, and just based on the name vector field and the fact that we spent all of last week talking about scalar fields, you could probably kind of guess what it is. Remember, a scalar field, it's a function that assigns to each point in space a scalar, right? So it's a function from Rn to R. Okay, a vector field is going to do the same thing, except instead of assigning to each point a scalar, it's going to assign to each point a vector, okay, like an arrow. Okay, so that's all it's going to be. It's going to be a function. This time, instead of from Rn to R, it's going to be from Rn to Rn, or maybe more specifically from some domain in Rn to Rn. Okay, that's all a vector field is. It's a function from some subset of the n-dimensional vectors to the set of n-dimensional vectors, okay? And it's important that the dimensions are the same, like the fact that this Rn is the same as this Rn here. That's what makes it a vector field, rather than just a vector valued function. Okay, and the key thing, like what this gets us, the fact that the input and output dimensions are the same as each other, what this gets us is the ability to think of this as like a collection of vectors on the plane, like what you're doing, or more generally, a collection of vectors in space. But for example, if n is 2, if the dimension is 2, then what's going on here is at each point in the input space, two-dimensional space, you're saying, okay, I'm going to plop a two-dimensional output vector on that point, okay? And like the way that it works is like whatever coordinate you're at. So like, for example, over here at -1, 1, I would be plugging x equals -1, y equals +1 into my vector field, and that would give me some output, and I draw that output arrow, that output vector, at that point, okay? And then if you do this for lots and lots of different points, draw lots of different arrows depending on different input values, you get sort of our natural visualization of a vector field. Okay, so let's do a couple examples. Okay, let's make things a little bit more concrete and actually do stuff with numbers. Okay, so let's sketch the vector field going from R2 to R2, defined in this way. Okay, so f of xy equals y negative x. Okay, and I'm going to start off just by plugging a bunch of numbers in. I don't know of a cleverer way to visualize a vector field at this point. Okay, so for example, maybe I plug x equals 0, y equals 1 in, so the point 0, 1. Well, that gives me the vector 1, 0, which I've sort of illustrated here. It's just the vector pointing straight to the right, 1 unit of distance, right? If I plug in 1, 0 into this formula, then the output is 0, -1. Okay, so that's the vector pointing straight down 1 unit of distance. If I plug in another point, -1, 0, I get the output 0, 1, so that's pointing up 1 unit of distance. And if I plug in 0, -1, then I get -1, 0 as my output, that's pointing left 1 unit of distance, okay? And maybe I just keep doing this over and over and over and over again. I plug in more and more inputs, and I get more and more output vectors, okay? And then at the end of the day, at each of those input locations, I plot the output vector. So for example, at the point 0, 1, so, over 0 units, up 1 unit, so up here, I plot this vector that's pointing straight to the right, okay? And then at the point 1, 0, I plot this vector that's pointing straight down, okay? So over here, the vector is pointing straight down. Down here, it's pointing left. Over here, it's pointing up. And then if I plot a bunch of the in-between vectors as well, like for example, at 1, 1, so now I'm at the top right, I'm up here, you can see the output vector, it's pointing down to the right, okay? And then I just plot all sorts of those, and I get my visualization of the vector field. And in this particular case, I mean, like sort of the way to think about this is the arrows, they're specifying motion. Like you can imagine, like what would happen if I dropped a particle or a ball or whatever into this vector field, and then its motion from that point forward was dictated by these vectors. Like you could sort of imagine, like if I dropped a ball or a particle over here, then this vector is telling it, oh, it's got to go this way. But then by the time it gets over here, now the vectors are saying, oh, it's going to go this way. And then now it's got to go this way and this way and this way. And you can probably guess that for this particular vector field, well, the particle would maybe just spin around and around and around, and maybe it's just going to go in a circle, or maybe it's going to spiral or something like that. You can't necessarily tell perfectly, but like if it follows the vectors, it's just going to spin round and round and round. And that's the way you should think about it. Okay, let's do another example, okay? And, our next example is going to be, okay, not the specific function you won't have seen before, okay, but the idea behind it you will have seen before. You've actually seen vector fields before, maybe not visualized like this, but you've seen them. You've seen functions from Rn to Rn. And one spot where you saw them was back in multivariable calculus, where you considered functions like this, functions from Rn to R. One thing that you did with functions like that was you computed the gradient of that function, right? And the gradient, remember, that was a function from Rn to Rn. So it's a vector field, okay? You didn't call it a vector field, but it was a vector field, okay, right? Because when you take the gradient of a multivariable function, like, right, what you're doing is you're taking the partial derivative with respect to each of those variables, each of the n input variables, and that gives you a vector output. And like still, each of these entries is a function of the n different variables. So now this is a function from, n entry vectors to n entry vectors. That's a vector field, okay? So we can do all of our vector field stuff with the gradient of any scalar field, right? So let's do an example like that. Let's suppose that we've got some scalar field, okay? So a function from R2 to R, okay? X squared times y plus 3 times y. What we're going to do is, first off, we're going to sketch just the scalar field like we did last week. Next up, I'm going to sketch a contour plot of this scalar field. Remember, a contour plot of a multivariable function of a scalar field, what it is it's a collection of lines, or a collection of curves, I should say, that tell you where the output, where the height is constant, where the output values of that function are constant. Okay, and then next after that, we're going to sketch the vector field associated with it. We're going to sketch, in other words, the gradient of that scalar field. Okay, so let's do this one at a time. We've got 3 things that we want to plot. We're going to plot them all on the same axes, but one at a time. Let's start with plotting the scalar field. Okay, and how did we do that? Well, this is from last week. We just plug in a bunch of values and plot those numbers, right? I mean, the output is numbers, and we just sort of draw dots on a grid, labeling each dot with the output value. Okay, so for example, if I plug in 0, 1 into this function, I'm going to get an output of 3. If I plug in 0, 2, I'm going to get 6, and so on. I just keep on plugging in values, and I get more and more output values. And then, I just go to a grid, and I say, okay, I'm going to plot dots with numbers as labels, as like the outputs as labels. And that's how I think of my scalar field. Okay, and that gives me sort of, I can sort of glance at that and say, oh, values are large in this region and small in this other region, and whatever. Okay, so that's what my scalar field looks like. Next up, contours. Okay, what does a contour plot look like? And the way you should think about a contour plot, its relationship with this scalar field picture is like you sort of imagine, like if you had infinitely many dots all over the place, then what you're doing is you're connecting the dots that have the same label, that have the same output value. Okay, and I mean, if I want to find actual equations for those curves, all I do is I say, okay, my scalar field, it's x squared y plus 3y. That output I'm going to be setting equal to some constant. And all I do is I rearrange and solve for y, just so that it's in a more familiar form and I know how to plot it. Okay, so if I take this equation here, solve for y, I get y equals c divided by x squared plus 3. And I mean, I know at least roughly what that looks like, right? Like it's going to be sort of one of these hump-shaped graphs where, like, okay, if x is 0, then you're at the top of the hump. And as x gets bigger, positive or negative, it's going to go down a little bit. And sort of the height of that hump is just dictated by c, by whatever the constant is. Okay, and if c is negative, that's just that whole image flipped. Okay, so that's what my contours look like, which makes sense with the scalar values that I plotted earlier. Okay, so that's what the contour plot on top of the scalar plot, scalar field plot looks like. All right, last but not least, what does the vector field, the gradient of this function f look like? Okay, and for that, again, I do the same thing that I've done a couple times now. Okay, I'm just going to plug particular values into this vector field. But before I can do that, I've got to know, okay, what is the vector field? I've got to compute the gradient. Okay, so I just take my scalar field, x squared times y plus 3y, and compute the partial derivatives. So this x squared times y becomes a 2xy. And then, when I take the y partial, I get x squared plus 3 in my second entry. Okay, so that's my gradient vector, and therefore that's my vector field that I'm working with. And now I'm going to plug a bunch of points into this, and I'll get output vectors. Okay, so for example, at the point 0, 1, like the scalar field had a value of 3, the vector field has a value of 0, 3. And then I just keep on doing this for more and more points. If I plug in 0, 2, I again get 0, 3, and I plug in lots and lots and lots of other points. And when I do this, I get a whole collection of vectors that I can draw on the same grid. And when I do this, like what's going on is this gradient vector, it's always pointing towards higher values, right? This is something that you actually learned in multivariable calculus. If you've got a scalar field, like what does the gradient tell you? The gradient tells you the direction of steepest ascent. In other words, it tells you, okay, if I'm on my scalar field, I'm at a particular dot with a particular label, which direction should I move in to go to a higher label as quickly as possible? That's what these vectors in the vector field are telling you. Okay, and so you end up getting a picture something like this. Okay, so the vector field arrows, they're just sort of pointing up the hill. Like if you think of this scalar field as a surface, then these vector field arrows are pointing up the hill. Okay, and I mean, another thing that you learned back in multivariable calculus is that this gradient vector, so these vector field vectors, they have a really nice property in that they're always perpendicular to the contours, which makes some sort of sense, right? Like if you want to go up the hill as quickly as possible, in other words, the gradient direction, you should go perpendicular to not going up the hill at all, which is the gradient direction, or sorry, which is the contour direction. Okay, so that's just from multivariable calculus, but it's useful to be reminded of that in sort of this new context where we're thinking of these as vector fields rather than just, the gradients of some function. Okay, and that's actually all we've got for today. Okay, so thanks for watching, everyone. I'll see you tomorrow for another one when we actually start doing things with vector fields.